All right, so now we've explored the idea of countable infinity, and we've seen an example of uncountable infinity in the last video with the set of real numbers. Now, it is pretty clear from that proof that we just went over, from Cantor's diagonal argument, it's pretty clear that countable infinity is like less than uncountable infinity, right? If it's uncountable, then it means that there's too many numbers to count, in a sense, right? You can try to count them, but you'll never be able to count them all because there's too many. So the size of the real numbers is like a larger cardinality than that of those other sets we were talking about, the natural numbers, the integers, the rational numbers. All of those are the same size. They're all, you've got over here in this count, in the countable infinity camp, you have natural numbers, positive integers, all the integers, you've got all the rational numbers, and then over here in the uncountable camp, you have the real numbers, as well as other things, which we haven't talked about yet. So all of these are the same size. Now, I want to talk about this because I want to then give you a list of numbers. So now that we've talked about this idea of like infinite sizes, infinite cardinalities, you can create this set called, it's like a collection, it's sort of a number system called the cardinal numbers. So the cardinal numbers function as a type of number system. There's two sorts of number systems that you hear bounced around sometime. You hear people talk about cardinal numbers, which have to do with size, and you hear people talk about ordinal numbers, which have to do with like ranking things in an order, like arranging things in an order. And they're different from each other, and the way that you think about infinity is a little different in those two contexts. So in this class, we're really just going to talk about cardinal numbers, the size of sets. And so here, possible cardinal numbers start with 0, right? You can't have a set with a negative number of elements. That doesn't make any sense. And you can't have like a fraction number of elements. You can't have a set with half an element. That doesn't make any sense. So we have 0, and then we have 1, 2, 3, 4, so on. These are going to give us, here we're going to have all of the natural numbers. Okay, those are all possible cardinal numbers. But then, after all of those finite cardinalities, you have the infinite cardinalities, and the smallest possible infinite cardinality is called Aleph null. Aleph is the first letter of the Hebrew alphabet, and it is used to represent the smallest possible infinite cardinality. This is the cardinality, this is countable infinity. So this is like the cardinality of the natural numbers. Countable infinity, this is Aleph null. Okay? Now, uncountable infinity actually includes everything which is bigger than that. Okay? If there's any cardinality bigger than that, then it's called uncountable. So everything beyond this. Now, somewhere along here is the cardinality of the continuum. So this is the this is the cardinality of the real numbers. This is like a fancy German letter C. So this stands for continuum, because the real numbers are called the continuum. So that's the cardinality of the real numbers. And actually, there is a question about what, if anything, is in between these. So here we have countable infinity. Here we have the uncountable infinity of real numbers. And is there any type of cardinality in between them? That actually is a weird and confounding question. So there is a famous thing in mathematics called the Continuum Hypothesis. And the Continuum Hypothesis says that there is no cardinal number n that lies between Aleph null and the cardinality of the real numbers. Like this. It says there's no cardinality n that satisfies this inequality. That it's strictly greater, like bigger than Aleph null, but smaller than cardinality. So that is a hypothesis. And the reason that is a hypothesis is that this statement is actually not only unproven, but unprovable in a sense, because it is what's called independent of the axioms, the ZFC axioms I mentioned when I was kind of talking about set theory and the foundations of mathematics and that sort of history. This statement is actually totally independent of the ZFC axioms. That means that you can assume the statement is true and you do not get a contradiction with the axioms. You can also assume that this statement is false and you still do not get a contradiction with any of the axioms. And if that's the case, what that means is that, in fact, it's impossible to prove or disprove this statement within our axiomatic system of mathematics, which is sort of mind-boggling. So we've got this notion of cardinal numbers, right? It's like these are the different possible sizes of sets, and then here we have countable infinity, and here's the real numbers, and in between that, we have no idea if anything is there, because it's impossible to prove that there either is or isn't. It's shocking. The only way you could prove that is to like find a set which is in there, and no one has ever found any set that would fall in between these. So in fact, most mathematicians believe the continuum hypothesis. They believe that there is nothing in between here. And if that's the case, if this is true, then what you get from that is you would then say that the cardinality of the real numbers, that special C, that letter that represents that cardinality, that would equal Aleph 1, which would be the next cardinal number directly after Aleph null. Okay? But whether or not that's true, you can't really prove it. There are a couple of other like theorems that I just want to mention related to some of this stuff. One theorem is that you can actually prove about this cardinality of the real numbers here. You can actually prove that this is the same as the cardinality of the power set of the natural numbers. Okay, so that is sort of an interesting theorem right there. So you might not be able to prove that it's the next largest size, but you can at least prove that it's the same size. There's a correspondence between the real numbers and the power set of the natural numbers. And this relates to something called Kanter's theorem. So Kanter's theorem says that, for any set A, the cardinality of that set A is strictly less than the cardinality of its power set. Remember that the power set of a set is like when you take all of the possible subsets of that set and use those as the elements for a new set. So we talked about how if you have a finite number of elements in your set, if it's the finite number n, if this is n, then the number of elements in the power set is 2 to the power n. I mentioned that in a previous video, because every element in the set is either going to be included in the subset or not included in the subset, and so you have two choices for each element, so 2 times 2 times 2 times 2 times 2 times 2, number of elements in the set is n, 2 to the power n. So that's like that's sort of how you could write that. You could say n is less than 2 to the n, and that's always true for every cardinal number. But what this has is a very interesting implication. So there's a corollary to this, which just says that there is no largest cardinal number. You can continue making larger and larger sets. And how can you do that? By taking power sets. I've run out of space on this paper, so I'm gonna flip it over and just write back here. So, say you want to find a set larger than the real numbers. Well, it's easy. Just take the power set of the real numbers. Think about the set of all subsets of real numbers. That is going to be something which is guaranteed by Kanter's theorem to be bigger. And say you want to find another bigger set after that. Just take the power set of the real numbers, and you're guaranteed that that's going to be bigger. ... forever, right? You can always keep taking the power set of the previous set to create a larger set. So the action of taking a power set to create a new set is something that guarantees you a bigger set. So there's no largest set. Sets can become bigger and bigger and bigger, and there's infinitely many different levels of infinity that are all uncountable levels of infinity beyond the infinity of the real numbers. So that's the end of the section. This stuff is definitely sort of this whole section 2.5 is almost like a tangent, just sort of we're dipping our feet into the world of abstract theoretical mathematics. But I think this stuff is just super cool and fun. it's fun to get excited about because the ideas of infinity are kind of like philosophically interesting and just kind of exciting to think about and talk about. So there's not a ton of application. In fact, there's really no application I'm aware of to computer science for this particular subject. But I love to include it in my class. I always include it in my class. So on the test, I might ask you to prove that two sets are equal in cardinality. So I might ask you to prove that, find a bijection and prove that it's a bijection. It won't be as hard, I think, as that one with the integers. But I might ask you to do that. I also might ask you to, tell me something about this continuum hypothesis. Sometimes I'll include like a true or false question, perhaps, about the continuum hypothesis, or some sort of like a short answer question where I ask you to explain something about this subject, because I want you to understand this at least. So that's the type of problem you can expect to see on a test. That's about it. I hope you enjoyed. We're going to turn our attention next to learning about counting, which is kind of a natural next topic to discuss after cardinality, because counting and cardinality kind of go hand in hand. But we are going to deal with counting finite sets and strategies for doing that in Chapter 6.